Good morning, good morning. Today some informations in English, in language similar to English, concerning relation between best directions of knapping of stones, mostly flints, and internal structure of various raw materials, mostly flints and obsidian. Some words about flints. There is a lot of various types of flints. They look very different from. They have various features from different sources, from different outcrops. And these features concern color and internal structure, crystallinity, and many other features. So there are examples of some selected Polish flints. And now some words, some informations concerning genesis of flints. Flints are mostly petrified, silicified sponges of various age, and there is many kind of sponges, many types of sponges, but there is a part of sponges is composed of this type of spicula, so-called spicula. This means needles of various shape, and these needles are built of silica, not crystalline, type of opal, and they make internal structure of spongia. And classification of some classifications of spongia and of flints are made due to type of needles of this spicula present inside. And sponges are living on the bottom of the basins, seas, lakes, etc. And of course they obtain oxygen from water, but they have very delicate apparatus for breathing, and if only appear traces of clay in water or start crystallization of calcite or other minerals, this system of breathing is blocked and they are dying, and after that they are covered with sediment, and next generation of spongia appeared on the bottom, and situation is repeated many times. As you see, there is a picture drawing of various type of needles present in the body of spongia. So this is example drawing showing the so-called hard ground type of bottom of the basin where are living sponges, and this is stage of transformation of organisms of sponges into the flints, into flints. And next, in geological profiles, where we are walking to the outcrops of limestones of various age, one can see the horizons of presence of flints. These horizons, there are horizons of presence of spongia on the bottom of old old basin many years ago. And situation, as you see, situation in this old basin was repeated. It was life of spongia and sedimentation of rock, mostly calcite, and next phase of life of sponga, and again and again. If sponga is dead, the spicula, the spicula made of silica, not crystalline silica, start to be alternated. Silica start to be changed to its water is removed from this silica, and it start to crystallize to chalcedony. And because of the pressure of rocks present over this horizon of flints, the flints start to be stressed by overlaying rocks, and during the crystallization of opal into chalcedony start appear small crystals of quartz, but these small crystals are growing in direction parallel to the direction of sediment. This means to the texture of sediment. Because of pressure, new formed chalcedony crystals are not growing to various directions, up there and there and there, but are growing because stress at this direction parallel to the sediment, structures of sediments, the stress is smaller than vertically. This is good for growing of crystal to the direction parallel to layering of limestones. So next, when we take the flint composed of chalcedony and we look carefully, one can see directions of the orientation of crystals of small crystals of quartz, chalcedony, and this parallel structure is the best direction of knapping. This means it's very difficult to destroy the flint when we beat from this direction, then we will beat from this direction. And if we start knapping to this direction vertically to the let's say crystallization of chalcedony, we are able to obtain small flakes, irregular. But if we start to work parallelly to this internal structure, we are able to obtain long blades, what was very important for prehistoric men. Together with this type of flints, and formed because of the orientation of new formed chalcedony crystals, there is other type of flint. There are irregular flints, shape is shown there, and these flints are crystallizing because of transportation of silica from completely dissolved, damaged sponga into the limestone. So, because of destruction of sponga, old sponga, removed silica is migrating across the limestones and start crystallization at some points where is the center of crystallization, grain of quartz or piece of other component. And these flints are irregular in shape in comparison with these layered flints. These are very irregular. These are regular, like nodules, similar to the bread, let's say, and these are very irregular. And crystallization of chalcedony in this type of flints is irregular. The crystals of chalcedony are growing there and there, like this and like this, and because of this, it's difficult to obtain good flakes, good blades from this type of flint. Because, for example, if we will beat this flint from this direction, we may obtain flakes of this size. Later, in this part, at this part of flint, chalcedony is orientated other way than there, so it's impossible to obtain flake or blade like this long. And there is the example of formation of core using nodular flint. At first is prepared the surface for knapping, and later both sides are produced blades according to the internal parallel structure, parallel orientation of small crystals of chalcedony. And in flints of secondary origin, very often prehistoric men obtain cores working from various directions, there and there and there. They feel, let's say, material. There are examples of blades obtained due to Maria Gurova, Professor Bulgarian, and this is example of irregular flint, the type of this type, let's say. Some words about the color. There is collection of flints from La Cime mountain over the King's Valley in Egypt. There is presence of horizons of flints looking like this, starting from the top. Not all are shown. There are plates polished, and you see there are various horizon, various type of flints. And this is flint from Poland, from village Goisz, Upper Paleolithic site, and these flints are mostly composed of chalcedony and opal, but these flints contain iron oxides. There are iron sulfides, mostly pyrite, marcasite, and because of presence of not oxidated iron minerals, reduced iron minerals, the color is gray, and in these flints color is brown, yellow is reddish because of admixture in structure of flint oxidated iron minerals. And there are examples of collection of various flints from Bulgaria, from various cities, various locations. There are names of sources of outcrops, and type of flint, Bulgaria, city Boch, flint 1, flint 2. And some words about the patination. At hot climate and dry climate, flints are patinated in brown, reddish, and sometimes near black color. In cold climate, flints are patinated with white patina. Why this situation take place? Because during the heating, during the day, the flints are heated at dry climate, and the rest of humidity with traces of elements are migrating from the center of flints to the surface, and because of heating insulation, water is removed and start crystallize minerals, oxides of iron, oxides of manganese, and this situation is repeated many times during day and night. During night it's cooler, during day it's very hot, and each day is migration of relics of humidity with dissolved iron and manganese. This humidity is migrating to the surface. Surface is heated, water is removed, start crystallized iron and manganese minerals. And because of this, at dry climate, we have dark patina. In cold climate, situation is other, because there is present other phenomenon. We have there many stages when water is frozen in the structure of flint, and next ice is dissolved to water, and again is crystallization of ice where is below zero, and dissolution of ice to water. And because of this phenomenon repeated thousand and thousand times, the structure of flint is damaged. This means the spaces between crystals of chalcedony are enlarged, appeared small spaces, small fissures, micro fissures below even 1 micrometer of diameter, and this destruction of structure of flint we observe as change of color because of the special optical phenomenon on the surface of flint. We observe the surface as white. There is no crystallization, there is destruction of internal structure of flints. There are examples of macro photographs obtained using polarizing light microscopy, and what we have opal, which is isotropic. It's not reacting in polarized light, and small crystals of quartz, and there is a scale. Next stage, we have chalcedony, this small gray substance of very small size crystals, and quartz, concentration of quartz, bigger crystals. This is of course flint too, recrystallized, and the relics of primary organic structure of sponga. There are relics of organic tissue of sponga, mineralized with quartz and chalcedony, of course. And in the center of this organic form mineralized with quartz, there are small concentrations of pyrite, iron sulfides, making this flint gray in color. There is example of flint which is completely recrystallized to the quartz. You see big, relatively big crystals of quartz. Of course, it's recrystallization of primary opal to quartz. It's this way: opal, chalcedony, quartz. No crystals, opal, small crystals, chalcedony, bigger crystals, quartz. And one can see there small inclusions, color inclusions. There are small crystals of carbonates, mostly represented by calcite. And this is a very beautiful example of flint, of organic structure of flint, preserved relics of tissue of sponga, recrystallized to chalcedony, special kind of chalcedony which is crystallizing in this form. Center is chalcedony of very fine structure, and around it's surrounded by chalcedony crystallizing as a fibrous and small admixture of color carbonates. Some words about obsidian and the best way of obsidian for knapping. This is a picture of implement discovered by Marcin Szela in Tominy, Holy Cross Mountains in Poland. Import from long distance, Winnicki border between Slovakia and Hungary. If we look more closer to the structure of obsidian using scanning microscopy, we may observe surface which was damaged because of the knapping, and natural eroded surface. This is primary surface. And what we have iron, traces of potassium, silica, of course. This is obsidian from Zemplin, near Winnicki. This is Zemplinskie Vrchy, on the border between Slovakia and Hungary. But if we look more closer to the structure of obsidian, there are only two examples. Obsidian from border between Slovakia and Hungary, so-called Carpathian. There are, as you know, 2 or 3 types, various internal structure, various chemistry. But if we look under the microscopy more closer to the structure of Carpathian obsidians, one can see evident parallel structure inside. There is more inclusions, various, as you see these small dark points, and there is less inclusions, but this structure, parallel structure, is repeated. And because of this, in obsidian, Carpathian obsidian, the best direction of best knapping is parallel to this parallel structure of obsidian. Of course, it's possible to obtain flakes when we will knap to this direction, perpendicular, but these products are small and irregular, and when we knap to this direction parallel to the structure of obsidian, we are able to obtain long, beautiful blades. And this is obsidian from Milos, and situation is similar, but inclusions are other. In Milos there is a few kinds of obsidian. In one kind of obsidian, sorry, one can see iron inclusions. It's mostly hematite, and as you see, it's orientated. These inclusions are present orientated way, and because of orientation of inclusions, the best way of knapping is parallel to this internal structure, to the presence of these internal inclusions. Other type of obsidian from Milos, this obsidian where one can see in structure small crystals of plagioclases, aluminium silicates, and because of crystallization during cooling of magma, these crystals of plagioclases are present orientated structure. So again, the best way of knapping, the best direction of knapping of this type of obsidian is to this direction, sorry, both directions, there and there. Perpendicular direction is not good. We are not able to obtain long, beautiful blades. And there is short summary concerning relation between internal structure of raw materials and the best direction of knapping. Please read this carefully and don't be hurry. And there is prehistorian man very happy. So thank you for listening, and please visit again this YouTube page. All the best. Thank you very much.